All right, so 5 is we have this fundamental theorem of calculus. This is the big shebang, and all it is it shows you that there is actually a connection between integration and differentiation. I mean, my first question would be so Cal 1, we pretty much just do derivatives. Cal 2, we pretty much just do integration. Are they two different things? And they're not. And you're going to see in 5.5 where you do substitution, you actually go back and do derivatives again. So they don't go away, even though I said, you know, your future class is going to be highly integration. And a lot of the things I see written too is a lot of trig functions. Okay, yeah, so you need to, you know, don't just say, well, I can integrate, you know, x squared, you know, something like that. Try to pick some harder problems. And what I'm going to do, it wouldn't let me extend it throughout the year, but your My Math Lab, you should be able to get into it till the end of this year with no problem. Meaning you could continue on in 5.5, 5.6, watch videos, get examples, print stuff out, whatever you want to do. So that way you would have some things that you could work on. All right, so not only does this connect integration and differentiation, which is the big thing, this says I don't want to do those rectangles. Okay, Riemann sum, you were pretty much, that's great that you learned how to do this to find area, but there's not, I don't want to just say an easier way, there's a more accurate way, and that's more important, and we do that with section 4.8, so certainly you can see why 4.8 is not on that test. It doesn't really go with that material. You just saw this, and I said it had a special name, and the special name is the mean value theorem. Those of you that have had statistics know that mean means the average. So this is the same thing. I'm finding the area and then dividing by my interval. All this is saying here is there is some point in this interval from A to B, you know, whatever my function looks like, somewhere in here from A to B, there is going to be a point C that if I evaluate it, that will actually give my average, the mean of this area. And so this is good to know. So now we move into using this for an actual, for an actual proof. Now we will get to functions, and I will get to that Friday, where if you want to find area below the curve, or below the x-axis, and some of you know that already, you just find it and absolute value it. But if you had area like this, and you took this area and this area, this would actually wipe that out. So we have to split this into two pieces and find area. Well, right now we don't care about that. We're saying if we're above the x-axis, then I can find my rectangle again, the area from A to B, and somewhere in here is going to be this C, which is going to be my mean height. And so this says, again, everything's wonderful if we have a continuous function. If I can get the height of the rectangle, then this will give me my average value. How do I find the height? I just evaluate it at that value of C. So that would be my f of C. All right, so be prepared to be astonished with this beautiful artwork. If you would like me to print this out and sign it, and you could sell it on eBay and make lots of money, because I could be famous. Well, I'm telling you, this artwork's pretty good. All right, so what I have is just some function. I say, well, within this function, I have some interval that I'm interested in finding area. It may not be the area of this entire thing, so I'm interested in finding. Well, let's say I cut it off right here, and I say I have some value of x. Well, certainly this, if I evaluate this function, if I want to get f of x, how I would find it is by this area. Notice that this area is going from a to x of this function, because this is my function here. Okay, so I can define this f of x as that area. Well, going back to the old days of this class, I can find that derivative. No problem with that, because I know this definition. So by looking at my definition again, then I'm going out further, x plus h minus my f of x, and I'm going to take that limit. Well, what I'm going to do is I'm going to show you that there's a connection between the derivatives and integrals. So I can replace this stuff. We just already said what f of x is. So I can replace f of x plus h. So everywhere you see an x, put an x plus h. which is what I did. So I replace these. This definition I already gave you. I can take that definition, replace this. My interval now is from a to x plus h. So that's all I've done here. I've done that math magic that says let these equal that. All right, now if I just look at the graph and I can say, well, if I'm subtracting this big piece and that big piece, that just gives me that piece here in the middle. Well, this blue piece here in the middle, notice that my limits of integration changed from x to x plus h. So this is the same thing as that numerator. There's nothing different there. This is just saying if I subtract these two areas, I'm going to get that blue area there. So I'm going to take this and I'm going to replace the numerator. All right, so nothing new. If I look at this function here and you can either pull the 1 over h out front, or looking at this is my area. This is the width of my interval, which is the same thing as my mean value theorem. I mean, there's nothing different. So in other words, this is the same thing as finding average value. But the difference of it is so I said my mean value theorem said if I have some interval here, now in this case, my interval has to be within here. I said I can find a C somewhere in that interval that I can find this average height by evaluating the function at f of c. Well, what this says to do, which hopefully is going to make sense to you, is make this width, instead of the width being that big, make the width get smaller. Head towards that x and make it get smaller and smaller and smaller. So basically, I get to this point here. I know my colors are getting hard to see. I get to this point right here, which if you remember, that's what we were doing when we found derivatives, is we were trying to just get to that exact point and make our width 0 connection thing. So if I say that there is some c that exists in this interval, then I can find, as I just mentioned, this is finding the derivative by taking the limit of this f of c by letting this width get smaller and smaller and smaller. Basically, I'm letting this go to x. Okay, so that's what it is if I let my c go to x, because I want this width right here to basically be 0. So if I let that go to x, then that says my width is going to 0. Or that's the same thing as saying my f of c is going to go to my f of x as x approaches 0. Well, if I look at this piece right here, and I say, oh, well, if I'm letting my h go to 0, take the limit of x as h goes to 0, take the limit of x plus h as h goes to 0. Well, that doesn't even depend on h, so that's just x. If this goes to 0, then that's just x. And so by my sandwich theorem, it says that my c is going to x, which by in turn says my f of c is going to my f of x. So all this means, well, it means two things. One, it means that there is a connection here between derivatives and my integration, my area. When I'm finding this area here, I'm still doing it by making my width smaller and smaller and smaller. And so this ties this together. Well, it also says, then why don't we find an easier way by taking these limits, making that width 0 to find that area, and that's your whole integration thing. All right, so this is this whole relationship that hopefully this kind of makes sense to you. If you remember when we looked at that and we said that's 4.8, where we ended it and says that's the same thing as integration, your antiderivative, we said that was actually, we were working backwards. You could say velocity, and we worked backwards to get our position function. Well, if we work backwards to get our position function, and notice here, this is with respect to x, in this case my interval, that's what's happening is I'm shrinking it, getting it to that actual value. If I do that, then I need to use this shortcut way of finding area by finding the original function, my position function, okay, once again my antiderivative, and evaluate it on this interval. So I have some interval that I'm going to plug these values in. So This now really gets to the part, well, again, we probably won't get too many problems, but gets to the part where you'll really be tested over, not that, all that stuff I went, again, that's just kind of background information, but to be able to understand how to find area by using this. This tells us how to calculate the area instead of doing a bunch of rectangles. But I just want to make sure you understand this is saying the same thing. Well, how do I find a rectangle area? The height times the width. What did I do? I summed a bunch of them. Well, what am I going to do? I'm going to take the limit and make the number of rectangles go to infinity. That's what that's saying. And it's just good to know that. I know most of you just jump here and go on your merrily way, but it's nice to go back here and say, well, that's really what the definition of this is doing. And then there's your 4.8. Well, let's see with some examples why this works. And I always tell students, find areas like my example I gave you of the half circle. Find something you don't need calculus to do, and then do it again with calculus. So why does this actually work? Well, let's say I have this function f of x equals 1, and I find the area at 0. So the height is 1, but the width is 0. So the area would be 1 times 0. So I put a point. So what I'm doing down here is I'm going to graph my area. I'm going to keep moving. Now I'm going to move to 1. So my area, notice that good scaling you got there. My area moves to 1 times 1. So at 1, my area is 1. If I this and I move to 2, then notice my area becomes 2 by 1, or my area is 2. If I draw a line through this, what is this function? Give me the actual y equals x. What's the antiderivative of 1? X. Yeah, or you could say what's the derivative of x? I know you're not there yet. Most of y'all working backwards. The derivative of x is 1. So it makes sense. It's like, oh, okay, well, this look at something else. There's my function. Is certainly something like this would be easy to do because I know I can find areas with triangles. So again, the area at 0, 0. Over, and I just draw a line at 1. Well, I know how to find that area. That's a triangle, 1/2 times base times height. So, and I put a point there. Again, this is my area being accumulated, I should say. And then I do this, and so my area at 2, and I start to get something that's starting to look like this. Continuing to do this, I can get my actual function, seeing what's happening here. Well, once again, let's write it in a better form. If I take the derivative of this, what's the derivative of that? 2x, or just x. And so you can see if you sit there and you graph the area that there is actually a connection with these two things. And you could continue to do this with, I mean, we could do it with 2x. We could plot areas here and see what's happening here just by even looking at the number to be able to work backwards to get our original function. So we can see that it works. But then again, we get to the point where we do the shortcuts and we say, well, if this is my antiderivative, what would I take the derivative of to actually? And so that's what we're trying to do, is we're trying to make a connection here between my antiderivatives and my original. So in other words, if I have this value and I take the derivative of it, I go this way, or if I have this value, I want to find the antiderivative, I go back the other way. Again, I hope, when we get to Friday, we're going to do a lot of this, because, yep, that's where I stopped my other class. So the only thing I can say is if this is new to you, try to not let this mess you up for the test on Monday. And that's all, folks.